Good day to everyone. My name is Chi Heng Tong. I'm here to present a paper on behalf of the team. The title of my paper is Ultra High Density SOIC with Submicron Bond Pitch. We are from TSMC R&D team. Just let me explain why we need the ultra high density bonding. Shown here is the Moore's law scaling. Moore's law tells us that the transistor count double every 2 years, and so if you put all the high performance computing system into the chart, including CPU, GPU, FPGA, and some of the accelerator recently announced, you actually find that it follows Moore's law quite nicely. However, there's one limitation here, is that the transistor count now reaching the limit of the wafer process 1 lithographic radical size, which is approximately 26 by 32 millimeter square. And so how do we continue such scaling to double the transistor counts every 2 years? Well, one way is to use the advanced packaging. And shown here some of the red data points, including the interposer and fan-out technology. The system, you actually see that it not only it can continue to the transistor count scaling, but it actually exceed what you can do within the SoC. And so how do we go about with the SOP scaling? Shown here is a new parameter we define as 3D ID. 3D interconnect density is defined by the number of lines per millimeter multiplied by the number of vertical interconnect per millimeter square. Take an example, the flip chip, what you can count is the number of solder bumps multiplied by the number of lines in the RDL, in the substrate. And so you can put all the existing packaging technology into this plot, and you find that the flip chip interconnect density actually fall behind the curve. What we show here is the doubling for every 2 years in interconnect density. And but with fan out and the interposer that recently people have a lot of discussion, it actually bring back the 2 years doubling trend. And so today we're going to talk about the SOIC and how SOIC can actually exceed the SOP scaling 2 years doubling trend. So for chip-to-chip interconnect scaling, SOP scaling, you have two approaches. One we call front-end 3D and one we call back-end 3D. Back-end 3D referring to the existing fan-out and interposer integration. And front-end 3D we're referring to chip-to-chip stacking, 3D IC stacking, whether it is chip on wafer or wafer on wafer. And by combining these two, we call it holistic 3D heterogeneous integration, where you can best optimize system PPAC, not just for Moore's law, but also for more than more heterogeneous integration. Now, the reason we call SOIC a front-end 3D is because it is based on wafer process, and because of that, it makes possible chip-to-chip interconnect pitch density go down to less than 1 micron. And this new bonding pitch density offer different integration density requirement and can satisfy different application domains need. So how do you achieve the sub-micron bonding density? There's a tremendous engineering effort need to be put in. Here are just examples of some of the key parameters and how they impact the bonding yield. Here are the cleanliness of the interface, the copper recess, CMP recess, and the copper barrier. Each one of them need to be optimized individually, and when you integrate them together, you also need to be optimized. And you can see that each one of them contribute to 30 to 50% of the bonding yield improvements. So there's a lot of engineering effort in such work. So for a good bonding, what you can see is whether the daisy chain, whether it's a very long chain or a very short chain, the resistance should be consistent throughout the bonding. Alright, so apparently for the 5-pitch bonding, one of the most important thing to do is to make sure the overlay misalignment accuracy is good enough. So what is good enough? Here the example shows that if the misalignment goes up, the bonding pair resistance goes up accordingly. And the conclusion we have is that you need to have for the sub 1 micron bonding, you need to have overlay accuracy better than 0.1 micron in order to get a consistent bonding quality. Same thing to the breakdown voltage between the neighboring pad, and shown here is the breakdown voltage versus the misalignment. Again, when the overlay is better than 0.1 micron, the breakdown voltage becomes stable and consistent, and with the highest value. And so for different daisy chain lengths, you should also get a very consistent resistant results. So with the robust bonding, the resistance increased linearly with chain lengths, as shown here, from 1K all the way to 9 million daisy chain. So submicron bonding, we put the same daisy chain in the test vehicle that we have, and different pitch density are demonstrated here with a very stable, resistant, and consistent high yield. Now, so not only the good quality and good bonding yield, you also need to make sure the bonding strength and the interface reliability, bonding interface reliability, are robust. So here is the stress migration test for the bonding that we have, and you can see that after 500 hours of stress migration test, the bond pair resistance remains the same. Same thing for the 1000 cycle thermal cycle. Excellent stability after 1000 temperature cycle. Now, so we also do the breakdown voltage and high temperature storage to verify the bonding qualities. And results shown here, they are very consistent, and results are very good. without any issue. So you have a very stable and high yield bonding. So what are you going to use it for? With such a fine pitch, you can enable the what we call the chiplet partitioning and integration. For the SoC chips, now the transistor scaling has encountered various problems. One of them is actually some of the circuits they are not appropriate or not easy to do the scaling. For example, the I/O or the SRAM. So there are a lot of discussion now talk about how you can partition these chips out of the SoC and reintegrate them using various integration technologies. So with ultra fine pitch bonding, you can enable deeper partition into the core area, and you can reuse the partition IP and use the legacy technology to manufacture them and then to integrate them back together. So reintegration can be 2.5D or 2.5 plus 3D depending on your system requirement and most of all the cost the cost benefit that you try to get from such scaling. So SoIC stacking is not just for face to face or face to back. It actually can do the multi-layer stacking. Or like so-called multi-tier stacking. So it enables the new computing architectures. One of the example is what we propose is the immersion in memory compute, or you can say IMMC. What it does is you interlace logic and memory using the SoIC stacking, and so you can optimize both the logic and the memory and get a non-good die and then reintegrate them using the SoIC technology. Here's a comparison tables that shows the traditional 3D IC using the solder micro bump, and also the SoIC using the 9 micron pitch and the sub 1 micron 0.9 micron pitch densities. So the solder micro bump, I think, is reasonable to assume that 36 micron is probably the high volume manufacturer limitations. And so you can see that using SoIC, you increase the bandwidth by nearly 200 times or even 20,000 times. And the power consumption has tremendous advantage. So here's the IMMC that I just mentioned. All right, so you interlace. Here you show the first layer is logic, memory, logic. Second tier is the memory, logic, memory. Third tier is the memory, logic, and so on and so forth. And in between you can have via to go through. If you don't want, you can just just go through the chips. So you can integrate multi-core logic memory with closest proximity. Not only logic to memory, but also logic to logic. And we believe this is particularly suitable for the machine learning kind of application. This is the ultimate near memory compute. It complementary to backend heterogeneous integration for best optimized performance, power, and area. And it's better average the existing ecosystem than the IMC, in-memory compute. Now the in-memory compute, people are still working on the hardware and software and architecture levels kind of studies. So it will take a while to actually realize them in production. But for this NMC, we believe you can leverage existing technologies from design all the way to manufacturing. So this slide basically summarizes what I just said now. We are using the front-end SOIC 3D integration plus the back-end fan-out and interposer integration technologies. So if you combine both, you can enable the new system integration with more power efficiency and cost effectiveness, and also you can integrate more functionalities into one system. And so backend 3D plus frontend 3D, and not only that, you can see that with the current SOIC plus info fan out, we can approach the